In part 2 of this series, we saw how simple geometry can be used to calculate the drop from the tangent line intersecting the Earth at point A to the dropped Earth at point B. This is useful for people who are studying the shape of the Earth, as it allows us to compare what we actually see across distances with what we ought to see if the Earth is a giant ball with a radius of 3,959 miles, as we are told by NASA. We also found that the results given by these geometrical equations accord with results given by Dubé's formula, i.e. 8 inches times the mile squared. In part 3 of this series, we will see how the drop can also be calculated using trigonometry. Geometry and trigonometry are both branches of mathematics, and they are intricately related, but there is a difference. In simple terms, geometry is concerned with the shape and size of all objects, whereas trigonometry is specifically concerned with triangles and, in particular, the relationships between lengths and angles. Of specific use to us are the trigonometric functions of sine and cosine. If you are unfamiliar with these functions, they may sound complicated, but in fact they are very straightforward. Put simply, for any right triangle, there is a relationship between the lengths of the sides and the angles between them, and sine and cosine are functions of the ratios between these lengths. When plotted, these ratios follow a simple pattern, and the sine-cosine functions are used to represent them. This allows us to calculate the relative length of one side of a triangle based purely upon the values of the length of another side and an angle. Although this can be done by hand, the sine and cosine functions on a calculator make the job even easier. The terms we need to know are the hypotenuse, the adjacent, and the opposite side of the triangle. The hypotenuse, as always, is the length which does not touch the right angle. The adjacent line is the one which bounds the angle in question with the hypotenuse, and the opposite line is the one which does not touch the angle in question. The sine of an angle equals the opposite divided by the hypotenuse. The cosine of an angle equals the adjacent divided by the hypotenuse, and the tangent of an angle equals the opposite over the adjacent. To utilize the sine and cosine functions, we need to know the angles involved in the calculations. The method for finding the angle is relatively straightforward, so long as we know the arc length. The arc length is simply the distance from one point to another along the circumference of the circle. We know from geometry that the distance around a circle, i.e. the circumference, is equal to 2 pi r. Note that pi itself is a mathematical constant given by dividing a circle's circumference by its diameter. For the angle in question then, it can be seen that x degrees divided by 360 is equal to the arc length divided by 2 pi r. We know this because the ratios must remain constant. There can only be 360 degrees in a circle, just as there can only be 2 pi r units in circumference of a circle. Therefore, the angle x and the arc length must be in proportion. We can thus set up an algebraic equation which will allow us to isolate the angle. X degrees over 360 equals a over 2 pi r. Then multiply both sides by 360. And then simplify the right hand side by dividing both the numerator and the denominator by 2. And we're left with x degrees equals 180 times the arc length over pi r. So we can use this formula to determine the angle bounded by two radial lines within a circle, so long as we know the arc length distance and the radius. To put it into practice, we will consider an arc length of 36 miles and a radius of 3,959 miles. As you can see, plugging those values into the equation, we're left with x degrees equals 180 times 36 over pi times 3959, which equals 0.521 degrees. With this information, we can now calculate the drop of the Earth at point B from the tangent. As with part 2, which used geometry, there are two methods we can use now with trigonometry. Distance from the tangent to the Earth at point B perpendicular to the Earth at point B, and distance from the tangent to the Earth at point B perpendicular to the tangent. Once again, from this point forward, the term tangent shall mean the tangent line intersecting the Earth at point A. First, we will look at the distance from the tangent to the Earth at point B perpendicular to the Earth at point B. In this case, we can imagine a triangle with hypotenuse length r plus d and adjacent length r. Using trigonometry and algebra, we can devise a formula for calculating d. Starting equation is the cosine of x equals the adjacent length over hypotenuse length. Then we multiply both sides by the hypotenuse. Then divide both sides by cosine of x. Then substitute in the algebraic terms. Subtract r from both sides. And then simplify further by factorising. We're left with d equals r, open bracket, 1 over cosine of x minus 1, close bracket. This is the formula we can use to calculate the drop from the tangent to the Earth at point B perpendicular to the Earth at point B. To put it into practice, let's use this formula to calculate the drop over an exemplary distance, say 36 miles. We can assume a radius of the Earth of 3,959 miles, as this is the value given to us by NASA for the ball Earth model being scrutinized. From the earlier example, we know that the angle x equals 0.521 degrees across a distance of 36 miles. By plugging these values into the formula, we get d equals 3959, open bracket, 1 divided by cosine 0.521 minus 1, close bracket, which equals 0.1637 miles, which equals about 864 feet. This means that the Earth at point B, 36 miles from point A, ought to have dropped 864 feet from the tangent perpendicular to the Earth at point B. We'll return to this later. Next, we will look at the distance of the drop from the tangent to the Earth at point B perpendicular to the tangent. In this case, we can imagine a triangle with hypotenuse length equals r, adjacent length equals r minus d. Using trigonometry and algebra, we can again devise a formula for calculating d. Starting equation, cosine x equals the adjacent over the hypotenuse. Then multiply both sides by the hypotenuse. Substitute in the algebraic terms. Add d to both sides. Subtract cosine x times r from both sides. And then simplify further by factorising. This leaves us with d equals r, open bracket, 1 minus the cosine of x, close bracket. This is the formula we can use to calculate the drop from the tangent to the Earth at point B perpendicular to the tangent. To put it into practice, we will again apply it to a distance of 36 miles across a circle of radius 3,959 miles. This gives us the equation of d equals 3959, open bracket, 1 minus cosine 0.521, close bracket, which equals 0.1637 miles, which again equals roughly 864 feet. You will have noticed that although these two formulas are measuring the drop in slightly different ways, they come out with very similar results. This is because a distance of 36 miles across the Earth makes an angle between radii from the center of the Earth of only roughly half a degree. So the distance between point B and the tangent is very similar regardless of whether that line is perpendicular to the tangent or perpendicular to the Earth below point B. Now we can compare the drops given by these simple trigonometric formulas with Dubé's formula. If x is 36, then 8 times 36 squared equals 10,368 inches or 864 feet. Clearly then, Dubé's formula gives results which align with simple trigonometry. We know from part 2 of this series that Dubé's formula also accords with simple geometry. In fact, all 4 formulas considered thus far, 2 geometric, 2 trigonometric, have yielded a result when used on the exemplary distance of 36 miles between point A and point B of 864 feet, the same as Dubé's formula. So it can be seen that Dubé's formula does indeed hold true and can be used to determine the drop of the Earth from the tangent to the Earth of the observer, at least over the relatively small distances for which it is commonly used, such as across lakes and bays. What happens if we use all 4 equations so far described, the 2 geometric and the 2 trigonometric, to calculate the drop over a larger distance, say 360 miles? It turns out that as the distance between point A and point B increases, the formulas begin to give diverging results. However, if you take the time to calculate the value of the drop for yourself using the 4 different formulas, you will find that even over 360 miles, the variance between the calculations is less than 1%. And how do they compare to Dubé's formula? Over 360 miles, the 8 inches per mile squared formula gives a result that sits neatly within the results of the 4 formulas in question. It goes without saying that even 360 miles is still relatively small compared to the alleged circumference of the Earth, and as the distance between point A and point B increases, gradually the formulas give results that diverge significantly from one another. However, Dubé's formula, even at a distance of 3,600 miles, still gives a drop value which is within 10% of the more accurate trigonometric formula. It has been shown that at distances typical of the kinds of applications for which it is used, such as the 36 miles example, Dubé's formula is strikingly accurate and accords with geometrical and trigonometrical calculations. Does this mean we ought to use Dubé's formula for the curvature experiments being conducted by increasing numbers of people on YouTube? No. As we will see in part 4 of this series, Dubé's formula, although very accurate for calculating the drop from the tangent, especially over relatively short distances, is not appropriate for the kinds of experiments for which some people typically use it. Put simply, this is because there is a distinct difference between drop and obstruction, and most experiments appear to be observing obstruction rather than drop. You'll see this for yourself in part 4 of this series, link in the info box below.